All right. Chemistry 1401. This is practice exam 3. Let's get started. On the first question, it says when hydrogen gas reacts with sulfur, hydrogen sulfide is formed when 1.20 grams of sulfur are reacted with excess hydrogen. 0.770 kilojoules of heat are released. How much heat is released when 2.50 moles of sulfur are reacted with excess hydrogen gas? What's it saying here? We're going to react hydrogen gas, H2 gas, with sulfur. Sulfur is a solid. We're going to produce H2S, which is also a gas, H2S gas. And it's telling us that if we react 1.20 grams of sulfur, we end up releasing 0.770 kilojoules of heat. So delta H is going to be equal to negative 0.770 kilojoules. Now you notice that none of the answers have a negative sign by them. The reason why is because when we see the word released, it says how much heat is released. That implies that it's negative, that it's exothermic. Okay? So anyhow, we don't have to have the negative in there since we know that heat is being released. We know it's exothermic. So it's kind of, the negative sign is taken up by the wording. Anyhow, but if we burn up that 1.20 grams of sulfur, we end up releasing that much heat. What's going to happen if we, burn up 2.5 moles of sulfur? Well, the answer is, this delta H, okay, is 0.770 kilojoules per how many moles of sulfur? Well, how many moles of sulfur do we have? We have 1.20 grams of sulfur, and we're going to divide that by the molar mass of sulfur, which is 32.06 grams per mole, like that. And we're going to get that the delta H for this particular reaction is going to be, and I haven't done this, so let me just get some quick math going here. So if I have 0.770 divided by 0.770 divided by 1.2 divided by 32.6, I end up with 20.6 kilojoules per mole of sulfur, like that. But if I'm going to burn up 2.5 moles, right? This is for 1 mole of sulfur. If I multiply by 2.5 moles of sulfur, I'm going to take that multiplied by 2.5, and I end up with negative 51.4 kilojoules. And that's per 2.5 moles of sulfur, but that's the amount of heat that's released. So 51.4 kilojoules of heat is released, and so this is closest. I must have rounded something off, but anyhow, 51.5 kilojoules of heat are released when we burn 2.5 moles of sulfur in the presence of excess hydrogen gas. Question number 2 says, which of the following depicts a situation where the least amount of work is done by a sample of a gas? If you read the possible answer, it says they all have to do with the expansion of a gas. When we want to calculate the amount of work done by gas expansion, we're going to use the formula work is equal to negative pressure times the change in volume. Let's look at the possible answers. A 20-liter sample of gas expands to 500 liters against a vacuum. A 1-liter sample of gas expands to 30 liters against a pressure of 2.22 atmospheres. A 20-liter sample of gas expands to 500 liters against a pressure of 30 atmospheres. And a 1-liter sample of gas expands to 30 liters against a pressure of 2.22 pascals. So we can see that we're given all the changes in volume, but we're given some different units of pressure here, aren't we? We're given atmospheres here and pascals here. I'd say that that's neither here nor there, because there's one of them that should stand out to you in terms of pressure. If I'm doing work against a vacuum, what's the pressure? If I'm doing work against a vacuum, my external pressure is 0 atmospheres or kilopascals or whatever. So when I plug my numbers into my formula, I'm getting -0 atmospheres, for example, multiplied by my change in volume, which is 500 liters minus 20 liters. Remember that delta V is equal to V final minus V initial. Well, that's going to give me 0, right? No work is going to be done at all. So no work done. And so the correct answer must be the sample that's expanding against a vacuum. Give me a thumbs up if you follow me on that one. It's a particular example that we did look at earlier on in the gases chapter. We talked about expanding against a vacuum, and we said no work is done. It was a particular example that I took from the book, I remember. Okay, cool. Well, let's talk about question 3 then. Question 3 says, which statement is true of the internal energy of a system and its surroundings during an energy exchange with a positive value of delta U of the system? Well, you should remember the formula for the change in energy, which is the same as delta U. Some textbooks use delta E, change in energy. Our book uses delta U. So delta U of the system is going to be equal to Q plus W. So you've got to be able to assign the sign of heat and work. If we look at the first possible answer, the internal energy of the system increases while the energy of the surroundings decreases. Well, in this case, if the internal energy of the system is increasing, that means that the Q is going to be positive, right? Heat is coming into the system. So that would give us a positive value for Q. And then it says if the energy of the surroundings is decreasing, that would mean that work is being done on the system by the surroundings, which would give us a positive value of work. That gives us a positive plus a positive. It's asking us when is the value of delta U going to be positive? This would have to be the correct answer because both the heat and the work values are going to be positive values. I just want to look at the second answer quickly. If you look at the delta U here, it says, what's the delta U when the internal energy of the system decreases? Well, in that case, your Q would be negative, while the energy of the surroundings increases. That would mean that work is being done on the surroundings by the system. That means you're adding two negative numbers. That means your delta U is definitely going to be a negative number. So that cannot be the correct answer. And then I quickly want to address the last two answers, which are the internal energy of the system and the surroundings decrease together, and the internal energy of the system and surroundings increase together. Both of those are impossible. If the internal energy of the system is increasing, the internal energy of the surroundings has to decrease, and vice versa. And so the correct answer is the first one. The internal energy of the system increases while the energy of the surroundings decreases. Again, when we add a positive number to a positive number, the delta U of the system is always going to give us a positive number. And that's what we're looking for. Question number 4. The reaction of sodium metal with liquid water is very exothermic. Sure, many of you have looked it up on YouTube or maybe even had the chance to try it yourself. It proceeds according to the following chemical equation. 2 moles of sodium plus 2 moles of water gives you 2 moles of sodium hydroxide plus 1 mole of hydrogen gas. And it's an exothermic reaction, isn't it? We'll release some heat, some fire maybe. Calculate the total energy released as heat when 245 mils of hydrogen gas are produced by this reaction, 0 degrees Celsius and 632 torr. Well, we know that this value, the delta H, negative 183.8 kilojoules per mole, is specific to this particular equation. That means that it's negative 138.8 kilojoules per mole per 1 mole of H2, right? Because there's only 1 mole of H2 in my balanced equation. Is 245 mils of hydrogen gas at this temperature and this pressure, is that 1 mole? Probably not. How are we going to determine how many moles it is? We're going to have to use the ideal gas law. PV is equal to N, or T, and our T, and we're going to solve for the number of moles of hydrogen. How can we do that? Well, we're given the pressure, 632 torr. We'll divide that by the conversion factor, 760 torr in an atmosphere, multiplied by the volume, 245 milliliters. There are 1,000 milliliters in 1 liter, so we'll divide that by 1,000, 0.245 liters. We'll divide by the gas constant, 0.08206 liter atmosphere per mole Kelvin. And then our temperature, 0 degrees Celsius in Kelvin, pretty easy calculation, 273 Kelvin. Let's double check our units. Torrs cancel, as do atmospheres, liters, and Kelvin, and we're left over with the number of moles of hydrogen. We get the number of moles of hydrogen is equal to 0.00909 moles. Well, now we can use that as a conversion factor. What kind of conversion factor, you ask? Well, remember, the delta H of my reaction, we know that negative 183 kilojoules is released when we produce 1 mole of H2. But what about if we only have 0.00909 moles of H2? Moles of H2 cancel, and we end up with our final answer, which is negative 1.67 kilojoules, 368. You see that all the answers are in joules. We know that there are 1,000 joules in 1 kilojoule, so if we multiply that number by 1,000, we get negative 1,670 joules. That's the amount of heat being released. Okay, let's try some problems that involve Hess's law. If you're given the following data, a bunch of equations here, I'll number them, keep things simple. 1, 2, 3 equations. It's asking us to calculate the delta H naught for a particular reaction shown right here. Well, how are we going to manipulate all 3 of these equations in order to give us this equation in the blue box? Let's look at some of the players here. If you look at equation number 1, it's the only one that has this molecule in it, C3H6. That's propene or propylene. I need 1 mole of that molecule, and again, it's only found in the first reaction. And so I'm not going to manipulate that reaction in any way. I'm going to write it out the same way it's written there. So we'll put equation 1 is C3H6 plus H2 gas produces C3H8. And we'll write down our delta H naught for our reaction, which is negative 124 kilojoules per mole. What about reaction number 2? Well, in reaction number 2, I have C3H8 gas, and it's the only place I see it besides right here. If you look at my equation in the blue box, I don't have any of that molecule. That means that I can't manipulate equation number 2 because I need these to cancel out when I add them together. And so I'm going to write down equation number 2 without manipulating it. You're probably thinking, aren't you going to do anything interesting here? Well, let's write it down. You see where it takes us. 5 moles of oxygen produces 3 moles of CO2 plus 4 moles of water. And the delta reaction is negative 2,220 kilojoules per mole. I want you to look at the last equation. And can anybody answer to me, how would I manipulate the last equation? Or should I even manipulate it? Could anybody tell me how it would manipulate the last equation? Okay, thanks, Violet. Perfect. Violet says reverse it. She's right. Let's cancel out what we can so far. You see that we have C3H8 the same on both sides here? Okay. Well, I need to get rid of my H2, don't I? I've got to get rid of that. And so the only other place that I find H2 or hydrogen is right here. So like Violet said, I'm going to have to reverse that. So I'm going to say multiply by -1, which is the same thing as saying reverse it. And so I'm going to have water in the liquid phase produces H2 gas plus 1/2 a mole of oxygen gas. I'm going to change the sign of my delta H, so I'm going to have 286 kilojoules per mole. Now I'm going to tally up those 3 equations to make sure that everything works out. As I said before, I can also cancel my hydrogen. I have hydrogen as a reactant here, and I have it as a product here. What else can I cancel? Well, if you look at water, I have 1 mole of water here, but I have 4 here. So I'm going to cancel the 4 out, and I'm going to be left with only 1. Or sorry, I'm going to cancel 1 out and be left with 3. 4 minus 1 is 3. What else? Is there anything else I can cancel? Well, I have 1/2 a mole of oxygen here. If I subtract 1/2 from 5, I end up with 4.5. There's nothing else that can be canceled. Let's watch carefully when we tally this all up. On the reactant side, what do we have? C3H6 plus 4.5 moles of oxygen. 4.5 is the same thing as 9 divided by 2. So let's write that down. C3H6 plus 4.5. And if you want to write 9 over 2, be my guest. Okay. What are the products? We've got 3 moles of carbon dioxide and 3 moles of water. Let's write that down. Now we're just going to tally up our delta H values. Plug them into your calculator. I've already gone ahead and done it. And you end up with your delta H naught of this new reaction as being negative 2,058 kilojoules per mole. Boom, we did it. Give me a thumbs up if you think you could nail that one. That's an important reaction, or that's an important question for Chemistry 1401 students. Very important question. Okay, I can promise that I'm going to ask some questions like this on the next exam and on your final exam as well. Question number 6. Which of the following equations represents a formation reaction? Formation reaction according to the standard enthalpy of formation. This is standard enthalpy of formation, delta H naught of formation. Well, what do we know about the standard enthalpy of formation? It's when we form 1 mole of a compound from its elements in their standard states. I'm going to give you a second, and if we label these, we'll call them A. Anybody have a suggestion? So which one of these is most reasonable? Jamil says B. I think he's in the right vein. If you look at the first one, H plus is not the standard form of hydrogen. OH minus is not the standard form of oxygen or hydrogen. If you look at C, chlorine is the standard, Cl2 is the standard form of chlorine, but PCl3 is not the standard form of phosphorus or chlorine. And if we look at D, we have 2 moles of sodium bicarbonate. That's not the standard form of sodium, hydrogen, carbon, or oxygen. So that can't be it. If we look at B, magnesium is a solid in its standard state. H2 is a diatomic molecule that's a gas in its standard state. Oxygen is also a diatomic molecule and exists as a gas in its standard state. So if we add all these up to form 1 mole of magnesium hydroxide, that equation represents the standard enthalpy of formation for magnesium hydroxide. Question number 7. Another question that uses Hess's law. It says use the following enthalpies of combustion from 1, 2, and 3 reactions to determine the enthalpy of formation of methanol. Well, what are we going to do here? If we look at the first reaction, it's the only place we see methanol. And there's 1 mole of it. So we're going to have to reverse the first reaction. So we'll put reverse first reaction. That's going to look like this. CO2 plus 2 moles of H2O gives you 3 halves or 1.5 moles of oxygen plus CH3OH liquid, delta H for that reaction. If I reverse it, I'm going to change the sign. So it'll be positive 726.4 kilojoules per mole. If I look at the second equation, it's the only place that I see graphite. And there's 1 mole of it, and I need 1 mole of it in my final equation. And so I'm not going to do anything to equation number 2. I'm just going to write it out as is. This is reaction. This is equation 1. Equation 2, again, I'm not going to change it. I'll put carbon, graphite, plus O2 gas gives me CO2 gas. The delta H of the reaction is negative 393.5 kilojoules per mole. And in the last equation, it's the only place that I have hydrogen, H2, but there's only 1 mole of it. And so I'm going to have to multiply this last equation, the whole thing, I have to multiply it by 2. So we'll say equation 3, we'll say multiply by 2. What's that going to give us? 2 moles of H2 gas plus 1 mole of O2 gas produces 2 moles of water. If I multiply negative 285.8 times 2, I get negative 571.6 kilojoules per mole. Now I'm going to tally these up. Let's look at the 3 reactions. You can see that carbon dioxide cancels out, as does the 2 moles of water. Something else that's interesting is on this side, I have a total of 2 moles of oxygen. Here I have 1.5 moles of oxygen. That's going to leave me with half a mole of oxygen on this side. Now when I tally all this up, I end up with carbon, graphite, plus 2H2 gas plus a half a mole of oxygen produces CH3 for methanol. And then I tally all these up. And when I do that, I end up with negative 238.7 kilojoules per mole. as my final answer. Looks good to me. Another question that deals with change in enthalpy. It says here, determine the delta H naught of a reaction for the combustion of cyclohexane described by the chemical equation shown here. Cyclohexane plus 9 moles of oxygen gives you 6 moles of carbon dioxide and 6 moles of water. Here are the delta H values for cyclohexane, carbon dioxide, and water. Why did they leave out the delta HF value for oxygen? Because delta HF naught for oxygen is equal to 0. Because O2 is in its standard state. Well, since we're given the heats of formation of these three compounds, the formula that we're going to use is delta H naught of our reaction is going to be equal to the sum of the stoichiometric coefficients multiplied by the delta H products minus the sum of the stoichiometric coefficients multiplied by the delta H of the reactants. Let's plug in some numbers. The delta H of our reaction will be equal to 6 times the heat of formation of CO2 plus 6 times the heat of formation of water subtract the 1 mole, the heat of formation for 1 mole of cyclohexane. Subtract negative 151.9. And then I'm going to add 0 to that because oxygen has no heat of formation. And I'll put all of this in kilojoules per mole. I left them out just to kind of save myself some time. When you punch all this spinach into your calculator, you end up with your delta H of reaction as being negative 2361 plus negative 1714.8 subtract negative 151.9 and kilojoules per mole for the whole thing. When you plug all that in, you get the delta H naught of this reaction is equal to negative 3,923.9 kilojoules per mole. For question number 9, we're given a bunch of average molar bond enthalpies. So this table here is just a bunch of bond enthalpies. It says use average molar bond enthalpies in the following equation to determine the molar energy of a carbon-sulfur bond. Again, we're given an equation and we're given the delta H of that reaction. Well, since we're given bond enthalpies, the formula that we're going to use is that the delta H of that reaction is going to be equal to the sum of the bond enthalpies of the reactants minus the sum of the bond enthalpies of the products. I'm going to have to move to a blank document in the interest of having a little more space. I have to delete some of this information here, I guess. Okay, let me delete this stuff. Okay. let's think about that reaction. I have CH3. I have CH3OH plus H2S gives me CH3SH plus H2O. Now, I want to write out the Lewis structures of all these compounds. So I'm going to take the time to write all the Lewis structures out. And that's going to help me determine what the bond energies or enthalpies that I need to use are. And there's a couple of different ways you could solve this problem. I'm showing you the long way. Last semester, I tried showing students the short way, and they didn't seem to appreciate it a whole lot. Okay, well, what bonds are we breaking? We're going to break the bonds over here. And then what are the bonds we're going to form? We're going to form these ones here. So, what are the bonds we're breaking? On this side, we're going to break 1, 2, 3 carbon-hydrogen bonds. Trying to find where I have that in my notes here. I left them out on that calculator. All right, since we're breaking 3 carbon-hydrogen bonds and then they're still here, those bonds weren't broken. So we're going to leave those out. Okay, we're going to leave those ones that I have highlighted. I'm leaving them out because to me it looks like they weren't broken or formed, really. Looks like they didn't do anything. The bonds that I did break, okay, so bonds that I did break, I have broken this bond and I formed this bond. So that means I've broken 1 carbon-oxygen bond. So I look at the bond enthalpy for a carbon-oxygen bond, okay, its bond enthalpy is 351 kilojoules per mole. This is its bond enthalpy. If I look at the bond enthalpy of the carbon-sulfur bond that's formed, that's what I'm looking for. So we'll say that's X. What other kinds of bonds am I breaking? Over here, I'm breaking an oxygen-hydrogen bond. So I broke at least 1 oxygen-hydrogen bond, which has a bond enthalpy of 464 kilojoules per mole. And on the other side, in the products, I formed 2 oxygen-hydrogen bonds. So that's going to be 2 OH bonds. And so that's going to be equal to 2 times 464 kilojoules per mole. I'm also, on the reactant side, I'm breaking 2 sulfur hydrogen bonds. So multiply that by 2. So that's going to be equal to 2 times 364 kilojoules per mole. And I'm going to form 1 sulfur hydrogen bond on this side. So let's put that down. I'm also forming 1 sulfur hydrogen bond, which is going to be 364 kilojoules per mole. So now I have all the bond enthalpies that I'm concerned with. So if I want to use this formula right here, I'm going to say that the delta H of my reaction, which was given to me, is negative 43.1 kilojoules per mole, is equal to the sum of the bonds broken, which is all these ones right here, it's going to be 351 plus 464 plus 2 times 364. I'll leave the units out because I'm going to put them in at the end. Subtract X plus 2 times 464 plus 364. And all of this is in kilojoules per mole. Well, the rest is just algebra in solving for the bond enthalpy of the carbon-sulfur bond. When you do this, you simplify to something that looks like this. Negative 43.1 is equal to 1543 minus X minus 1292. Of course, everything is kilojoules per mole. And then when you solve for X, you find that X is equal to 294.1 kilojoules per mole. So we're just using a little bit of algebra to solve for X, which was the bond enthalpy of the carbon-sulfur bond.